We're going to use a calorimeter to try and figure out the identity of a metal based on an experimental specific heat capacity. So we need a pure metal sample. We need to know its mass. The shape doesn't matter. Place this metal object into an open beaker filled with boiling water and allow it to sit. We allow it to sit until all of that metal is the same temperature as the boiling water. We know what the water temperature is, 100 degrees Celsius. So now we know the temperature of the metal. So now comes the key step. As quickly as possible, you take the metal out of the boiling water and transfer it into a beaker, our calorimeter, which holds 50 milliliters of some much cooler water, let's say 24.4 degrees Celsius. And we know that because we measured the temperature with a thermometer. The hot metal will cool down, the water will heat up until they both get to the same ending temperature. You use the thermometer to find out what the final temperature is. Let's say it's now 27.2 degrees Celsius. And now you have two different delta T values. One is your initial temperature of the hot water minus the ending temperature. The other is the ending temperature minus the 24.4 degrees Celsius for the water. So let's write down our situation and start solving this problem. So we have information for our metal, the mass of our metal, the initial temperature when it was in its boiling water bath, 100 degrees Celsius. We don't know the specific heat. That's what we're looking to find out. We know information about the water. If you start with 50 milliliters of water, the density of water is 1 gram per 1 milliliter, so that means we have 50 grams of water. We know the initial temperature of water, we know the heat capacity of water, and we know the final temperature once they've come to an equilibrium temperature. At this point, we're going to make an assumption that all of that heat from the hot metal has been transferred to the water. We didn't lose any heat to the air, and we're going to assume our calorimeter isn't absorbing heat itself. Even though it does absorb a little bit of heat, it's a negligible amount for us. In an actual experiment, the heat transfer will never be 100%, but for our purposes, we're ignoring all of this, and we're going to use conservation of heat to help us solve this problem. We're assuming that all of the heat that flowed from the metal to the water has been conserved so that we can write a simple equation like this. We use MC delta T for both heat expressions. This is the mass of our metal, heat capacity of the metal that we don't know, and delta T for the metal. And that is going to be equal to mass of water, heat capacity of water, times the change in temperature for the water. So our changes in temperature are going to be different. We're using T initial for our water here, same temperature final. The metal started off at a much higher temperature. Now we can fill in some numbers that we know. The mass of our metal, heat capacity is something we still don't know. Final minus initial temperature. So final is our 27.2 degrees Celsius. Initially we were at 100 degrees Celsius. We know all the information required to solve for the heat that was gained by the water right here. So I've just solved for our heat capacity of the metal. Notice the rather small temperature change for the water and the very large temperature change for the metal. That's typical because metal has a very small heat capacity, much under 1 joule per gram degree Celsius, and water has a very large heat capacity. This experimental heat capacity is very similar to lead, so that would be the identity of our mystery metal.